Hello, we are the NASA Indoor Farming Senior Design Team. I'm Lauren, the project manager.
I'm Greg, the structural.
I'm Sean, computing and electrical.
I'm Spencer, I've been working on the plants and the CFD. I'm Luke, I'm doing CAD and construction.
I'm Allison, and my main focus has been the irrigation system.
Our team was very drawn to this project due to the unique problem which needed to be solved: designing an automated indoor farm to grow crops for astronauts aboard the ISS and also in future long-term space missions. To construct such a system, our goals for the design of the indoor farm consisted of the following: automation and real-time monitoring of temperature, humidity, lighting, and nutrient water delivery, minimization of water usage by selecting aeroponics for irrigation, and modularity to decrease payload launch mass, size, and cost. By setting these goals, we could plan how we wanted to meet deadlines and tasks. We decided to plan our project by breaking our overall design down into smaller systems. These critical subsystems included structural, electrical, lighting, temperature and humidity, crops, air circulation, and irrigation.
See the aluminum frame that we designed in Fusion 360? It acts as the backbone for the whole structure. All of the various sub-assemblies mount up to it. This is the central waterproof container. It's sealed with silicone on all sides. Within it are the misters for the irrigation system, the fan for air circulation, as well as the diaphragm valves that we use to seal the box. Using magnetic tape and a series of magnets mounted within the tinted siding, the walls can easily be removed and replaced for maintenance, planting, or harvesting of the vegetation. The LEDs are mounted to the top piece of acrylic, so they are also easily removable for maintenance. This is the model for the 3D printed electronics box that we designed. It houses the Arduino and various electrical components to keep them away from any stray moisture. This is the 5-gallon reservoir we picked for our nutrient and water mixture. You can see the feed tube was designed to run all the way down to the bottom of the reservoir to ensure that all 5 gallons can be used.
So for our FEA analysis, I pushed the limit, which far exceeds whatever the actual structure will withstand or sustain in true use. But I pushed these here to 10,000 newtons. I pushed it so high because the factor of safety of our structure is so high that 10,000 showed that it actually does move and it's not just 15. So we used for our structure T-extruded 80/20 aluminum. This material is very strong. It has a lot of lightweight properties and it's an anti-corrosive material. So any of the nutrients, the water, any other element that may adhere to the metal won't corrode it as fast or as badly as other materials. So we use these valves here. A theoretical implication, this will help reduce the pressure within the bulkhead and release some of that pressure that builds up. And then it will release some of the excess moisture that's in the bulkhead in the form of humidity, which will then be released to the ISS, and the ISS, a water reclamation system, can then reclaim that water and use it for future use. Finally, we added tint to our acrylic panels. So we used acrylic because it is very impact resistant and it won't break like glass, and it will still stay clear, and it's UV resistant. So it's not going to yellow or anything like that. We added tint to it to add for light reflection so it reaches all of the plant very well. It allows for easier viewpoints so that it is easier to see in because the LEDs are very bright. Allows for clear view to be able to see if there's any diseases happening or something's wrong. It allows for an illusion of there seeming like there's more plants than there actually are.
Stepping into the mechatronics and control sides of things, this here is a wiring diagram of our main control structure, monitoring many of the life support systems such as the pump and nutrient delivery, the lighting, the day-night cycle, and the fans for the air and cooling, environment control for the plants. Other than the wiring and figuring out how to connect everything together, probably the most difficult part of this was figuring out how to power everything. A lot of these components require unique voltages, and some of them weren't even standardized. Like the LED lights, for example, ran off of like 20.8 volts to run efficiently. So that was a pretty interesting problem to figure out. Not to mention that the pump runs off of AC power and the rest of it runs off of DC power. So just an interesting problem to solve. Moving on, we have coding diagram here. This is a flow chart of how the code essentially runs and operates. It starts off by initializing all the components and activating them, and then it jumps into essentially a giant loop that just constantly goes around and reads time from a real-time clock unit. After that, it just basically like checks the time, like, oh, is it time to activate the pump? Is it time to do the lights? And these intervals can be changed for whatever plant we're trying to grow. In our case, it's kale. The last part of the loop was just reading temperature sensors and humidity sensors, reporting them back to the Arduino, where then it would report to the LCD screen to where it could be displayed and monitored by people. This here is a picture of the electronics box. The first floor is a lot of the power supply and distribution with a few miscellaneous components here. The second floor would house the Arduino and a lot of the wiring for the control structure up there. Here's a picture of the LED lighting being turned on and the humidity and temperature sensors being activated and displayed on our LCD screen. This is a finalized picture of everything enclosed and encased inside of the electronics box with the LCD and the keypad sitting there right there on top.
So we decided to go with kale for our plant of choice. The main reason for this is kale is very hardy. Definitely as we're testing things out and putting it under different situations, it will definitely last the best and live the longest. The only downside to kale is that the taste is not very good. We actually talked to some people from NASA and they told us that kale was at the bottom of the list for tasty vegetables. However, they did say that red Russian kale was actually the best tasting, which is why we went with that one.
Here we have our plant housing for the system. Our system holds 4 plants. The plants are placed in these neoprene clone collars after being grown in the germination station to the swarm of sprouting. The clone collars are then placed in the net pots, which all of these items do provide stability for the plant. The clone collar helps the stem with stability, and the net pots were implemented for stability of the roots. As they grow, it wraps around the net pot and helps stabilize those roots, as well as blocking the roots from getting to the sprayers, tangling up the sprayers and causing clogging.
We conducted a CFD simulation of the fan airflow. And so this is important for our project because in microgravity, water will actually accumulate around the leaves of the plant, which means that they won't be able to transpire. They won't be able to respirate. And so they'll actually just die if there's not good enough circulation. So we just ran a test circulation with the fans that we were going to buy and just made sure that there was enough coverage, which as you can see on the picture on the right, there's definitely enough coverage around the leaves. The picture on the left is just a better demonstration, so you can see further in the back. We also performed a CFD analysis for the internal flow of the water. And so this is important because we just want to make sure that the store components that we had picked out before we actually spent the money on that and the pump, if these would get to the velocity required in order to spray the plants consistently.
Here's the irrigation system and how we provide water to our plants. We went with an aeroponic system because it has very high water efficiency, which was a major need for our system. We have our T-threaded nozzles, which have 2 nozzles directed at each plant's root system, directly at the roots to get as much water as possible on the roots, as well as filling up the bulkhead with enough water to create 90% humidity, which was necessary for the growth of our plants. So those T-threaded nozzles are connected with the 1/4-inch tubing. The elbow corners were implemented to create the shape so it fit best into our box system. The bottom left shows the connector that goes through the tubing to the pump, which I will discuss later. This system, we have a video testing and showing the spraying directly after this. This is the pump we use for our system. It was chosen for adequate flow rate and pressure needed for our system. And then here is our reservoir, simulation reservoir. For the theoretical design, we would use the ISS's water. Based on water calculations, it was decided that 5 gallons was more than enough to keep it running for a couple of weeks, so it would not need to be refilled very often. And then all plants need a certain amount of nutrients. The reservoir will have distilled water to have it be as close in simulation to the ISS ultra pure water, and that strips the water of all the nutrients that plants would normally get from either the water and the soil, which also our system does not have soil. So it is very necessary to have this nutrient mix. It provides nutrients such as nitrogen, phosphate, calcium, and magnesium, all necessary for adequate plant growth, which the ratio is decided based on the nutrients that we got. Finally, this is our germination station. It was discovered that it is not possible to pre-germinate the seeds to send up to the ISS due to shelf life, unknown shelf life, and the sprouts would most likely die before being sent up. We created a station where the seeds would be able to turn into sprouts. And as you can see, On the left image, I did start a couple of different plants, all leafy, all very good for crops, being able to keep the plant growing as you take the crop leaves away. The seeds are put into these growth sponges into the trays and closed into the drawer here. Those sponges can then be placed directly into our system. So that makes it a little easier to be implemented in the system for astronauts.
As you can see, we have made significant progress with our prototype. We still have some future tests we need to conduct, including calibrating our humidity and temperature sensors, testing the voltage of our electrical system, and validating our irrigation system functions properly. As for the stakeholders regarding our project, NASA and other national space agencies will all benefit. They will be able to provide fresh, nutritious vegetables to astronauts on missions. Our prototype design would serve as a stepping stone for our theoretical system, which would be implemented and tested on the ISS. We also believe our modular aeroponic indoor farm could be accessible in people's homes and communities, which would yield agricultural and health benefits. We look forward to meeting you at the Senior Design Showcase. Thank you.